Okay, chapter 12, fluid dynamics and its biological and medical applications. So now we're going to talk about, we got fluids, we had them in static cases and so on. Now let's talk about what happens when you put fluid in motion through a pipe or some other things. So we're talking about flow rate, its definition, and then Bernoulli's equation, which is sort of an energy formulation of water, and then basically some applications of these things. So flow rate is basically the volume of water passing over a certain amount of time. So what is volume? It's area times height. Okay, so if that volume of water passes through that point in a certain amount of time, that's volume flow rate. It's just volume over time, which is area times d. So area times d over time. And as you know, distance over time is velocity. So you can think of flow rate as the area of the pipe or the water times the velocity of the water flowing through the pipe. Okay, so the units here for volume is liter. That's the unit for volume, and the flow rate is meters cubed per second. So sometimes we use liters, sometimes we use whatever, centimeters cubed or some other unit, but it's meters cubed per second is the SI unit of Q of flow rate. Okay, so that's the definition of flow rate. If you have this amount of water flowing that distance in that time, that is flow rate. Okay, now question is, so here, well, let's just do an example. How many cubic meters of blood does the heart pump in a 75-year lifetime, assuming an average flow rate of 5 liters per minute? So the strategy is that time and flow rate are given. We've got 75 years for time. We've got a flow rate of 5 liters per minute. And so we want the total volume, and we can solve for that and take the flow rate times time and do your unit conversions, and then you get that amount of blood, which is a lot, 200,000 tons of blood. That's equivalent to about 200 times the volume of water contained in a 6-lane, 50-meter lap pool. Okay, going on, water flow rate. Now the thing is, there's a continuity equation here, which is the flow rate through this part of the pipe has to equal the flow rate through that part of the pipe because they're connected, and all the water flowing here has got to go somewhere, so it's got to flow through that pipe in the same way. So this volume of water is the same volume of water here. The difference is the water has to speed up in order for that same amount of volume to pass through in the same amount of time. Since fluids are not compressible, they flow and push into each other, and so that's how this works. So the continuity equation says if you have this area and that velocity of water flowing here, then if you go to a smaller area, you got to have a higher velocity there to manage the flow rate. Okay, so A1V1 is equal to A2V2. So that's your common problem to solve now, is you've got an area, a pipe with let's say they give you the diameter of the pipe, but what is your problem? You got to convert that to an area, so the area is going to be pi times the diameter divided by 2 squared, pi r squared, and the radius is half the diameter, okay? And then once you get that area, if they tell you the velocity of the water, then you can calculate the area and the velocity over here. Sometimes they'll give you the flow rate, and then you got to calculate the velocity or the area from that. So just keep all those things in mind. You could have Q1 is equal to A2V2, or A1V1 is equal to Q2. So a bunch of different permutations of those equations there. Okay, so yeah, so here you go, a nozzle with this radius attached to a garden hose. With that radius, the flow rate through is this. Calculate the speed of the water in the hose and in the nozzle. Okay, so you just solve for the velocities. Since the area is the only thing that's changing, the flow rate is the same in each part of the hose. The only thing that's changing is the area. So you get that it's about 2 meters per second in the hose and about 25.5 meters per second coming out of the end. And this is why when you put your thumb on the edge of the hose, it just shoots out, and that is, whatever. Okay. Blah, blah, blah. We got a blood vessel there, another example. Okay, so Bernoulli's equation says that at any point in a fluid, there's something that's conserved. And what's conserved is the combination of the pressures, the kinetic energy of the fluid, and the potential energy of the fluid. So you got the pressure at some point in a pipe plus the 1/2 rho v squared, and for a fluid the density is kind of the mass term, plus rho gh, which is like mgh, or 1/2 mv squared. Those combinations are constant. So that means if you're at some point in a pipe and you go to another point in a pipe, these two values are equal to each other. So if your velocity changes or you change your altitude or your height, your pressure is going to change too, in order to make sure all these things are equal to each other. Okay, so that's our conversion factor. If the fluid is not changing height, or sorry, if the fluid is static, so you just have a pipe that's going up in height, but the water is just sitting there, then the pressure here is P1 plus rho GH1, and you go up to H2, you're going to have a different pressure because now your kinetic or your potential energy is a little bit different. Okay, so you can solve for the pressure at some other point. If you take, H2 to be 0, for example, then you can calculate the pressure deeper in the fluid, and it's just your normal rho GH equation that added to your thing. If, however, the heights don't change and you want to calculate the pressures at 2 points in a fluid where, the pipe narrows, then the pressure in one point here is equal to the pressure over there. And we know that the velocity here might be lower. And when it goes into that narrow pipe, the velocity shoots up. And so that means the pressure has to go down in order to keep those two equations equal. So in this hose where the speed went from 1 to 25 meters per second, we want to calculate the pressure. And so we know we can calculate the pressure. It's the pressure at the other point plus the change in energies here. And the height we don't have in our equation because it's not changing height. Now, what you have to remember is when water comes out of a hose, okay, as it comes out of the end of the nozzle, it's entering the atmosphere. So the pressure at the outlet of a hose is generally 101,000 pascals. So you add that in there, and then you get the pressure inside the pipe there to be this amount of pressure. Okay, and so the absolute pressure in the hose is greater than the nozzle as expected, right? It's going to shoot out of it, and the pressure P2 has to be 1 atmosphere because that's what it emerges out to. Okay, so there's some applications there of Bernoulli's principle. You got an airfoil, and you got a boat, a sail there, showing you how the pressures can be different because the velocities change. So the higher velocity, as you fly faster over the wing, the air over the wing travels faster, so it has a little bit lower pressure and a little bit higher pressure underneath. And so that imbalance of pressures gives you a net pressure up. Okay, and then you got, some tubes here, some other applications of it. The most general application is Torricelli's theorem, which just says if you've got a tank of water, right, open to the atmosphere, and then water comes pouring out of it at the bottom, which means it also has the atmosphere on it, so P1 and P2 are equal, then the velocity of the water shooting out of it is just the velocity of the water coming in plus 2gh. So you can solve for the velocity of the water shooting out of this thing, where h is just the height of the water that fell. So let's say you've got a dam, right, and you got water shooting out of the bottom of this. You can just calculate how fast the water would be coming out of the dam. It's just 2gh plus v1 squared, and square root that. And so we've got an example here with a fire hose. Calculate all these things, the pressure coming out of this hose. And the thing is, they tell us the gauge pressure here. So they tell us that the pressure is just the gauge pressure. So we don't have 1 atmosphere already in. And since we don't have 1 atmosphere already in, P2 is going to be 0 because we're ignoring the atmosphere. The change from the inside the hose to the nozzle, you go from the gauge pressure, P gauge, and then out here is 0 relative to that. That's what gauge pressure tells you. And so normally this is the absolute pressure outside is 1 atmosphere, but since they didn't tell us the absolute pressure inside, which would have 1 atmosphere added to it, they told us the gauge pressure. Then in that case, you have to take the pressure when it emerges to be 0. Okay, so this is your tricky point here. If you've got a hose and the water emerges outside and they tell you the absolute pressure, then the absolute pressure is going to be 1 atmosphere plus the pressure of the inside of the hose, okay? And then when it comes outside, the P2 is 0, or not P2, but the pressure outside is 0, and then the absolute pressure is just 1 atmosphere outside the hose. If they just tell you the gauge pressure, they're only telling you the pressure relative to 1 atmosphere, and so then when it goes from inside the pipe to outside the pipe, it should be the difference of that pressure should just be the gauge pressure, and so the secondary pressure should be 0. Okay, so that's a little bit tricky, but that's okay. So viscosity, laminar flow. So this is an example. We've got nice laminar flow at the bottom of this, and then it starts to go turbulent and go all over the place. So those are the differences between the types of flows. In everything we talked about so far, we've considered laminar flow. Turbulence is a little bit, difficult to model and calculate, and you just get all these things and rapids on the river and so on. And we're not going to go into any of this in any detail. So a non-viscous fluid is also what we've been considering, and the flow rate is, this nice straight lines. A viscous fluid is going to stick to the container walls, and so it's going to move faster down the middle and kind of slower on the ends. And you can imagine honey or something like that, and you can see the two examples of nice flow here, and this one is just sticking to the air basically, and the center of it is emerging higher, but the edges of it are slowing down. Okay, but other than that, we're not going to deal too much with viscosity or the other things, so you don't have to worry too much about that. Turbulence, again, the onset of turbulence, when you go from laminar to turbulence, it's anytime you change that area. There's the Reynolds number here. Again, you don't have to worry too much about this. We're not going to dive into that. And we don't have to deal with the motion through a viscous fluid. Any of that stuff. And yeah, we're not going to deal with this either. Okay, so you don't have to worry too much about that. It's just a little bit too in-depth, a little bit too much for what we're after here. I definitely recommend you reading it and just kind of being aware of it. You never know when you're going to need it. Okay, so in summary, we got our flow rate, Q. That's volume per time. Remember, volume is area times length, or area times height, or something like that, and that'll give you your volume. And the continuity equation says that the flow rate through a fluid is constant. And so if you have the flow rate at any point in the fluid, in the pipe, it's equal at another point in an enclosed pipe, and the flow rate is just the area times the velocity. So you can calculate the velocity of a fluid anywhere in the pipe just by changing the diameter of it. Bernoulli's equation is the conservation of energy kind of formula of fluids, and it tells you the pressure at some point in a pipe is the kinetic energy term plus the potential energy term, and that whole thing, those three numbers added together, is constant. So that means at any other point in the pipe, it's equal to each other. Okay, and then P1 is 1/2 rho V1 squared, P2 plus 1/2 rho V2 squared, and so on, and you get all this stuff. So the most general applications of Bernoulli's equation, you've got your power in fluid flow is given by this equation. We're not doing 12.3, 12.4, 12.5, 26, 12.7. You don't have to spend time on those ones. Okay, so just be able to calculate the pressures at some point, the velocities at different points. One last comment: you generally use the continuity equation to calculate velocities, and then once you get the velocities, you can plug it into Bernoulli's equation to get the pressures. So that's your general strategy, or vice versa. You're given the pressures, but then you need to calculate the velocities. So you can use Bernoulli's equation to calculate the pressures, and then go backwards and use this equation to get the velocities. Okay, let's see. Yeah, that's it. Talk to you later. Bye.